Ladies and gentlemen, welcome to Chapter 6 of our second year level course in Structural Geology. In this chapter we are covering convergent tectonic settings, and in the first part, which is this video, we are discussing convergent plate margins. In the second part we are going to talk about continent-continent collision in a separate video. The intraoceanic settings that we see here can be subdivided into migratory, detached and stationary settings, and the migratory and the stationary setting have in common that an island arc is formed by intraoceanic subduction, and here we see volcanic arcs, island chains forming from differentiated mantle magma that rises to the surface from the top of a subduction zone. The difference between the migratory and the stationary arcs are the tectonics in the back arc. In the case of the migratory back arc, we find oceanic spreading, back arc spreading, where new oceanic crust is formed. In the stationary, we do neither find contraction nor extension in the back arc oceanic crust. The detached setting that we see here in the middle is pretty much the same like the two other settings, with the difference that the arc is not formed by differentiated mantle magmas alone. We find here a sliver of continental crust that has rifted off a nearby continent in an earlier episode of tectonics. This episode would have formed the back arc basin that we see here. Examples for these are mentioned here: the Marianas, Tonga, Kermadec, and the Scotia arc. Japan, of course, is an important example for a detached setting. The Aleutians are stationary, and here we see a map where we can find these places. Here in the Aleutian arc we find subduction of the Pacific crust underneath the North American plate, and we can see here there is old oceanic crust forming an abyssal plain in this region. There's also some continental lithosphere that connects Alaska and Russia, but there is neither extension nor contraction seen currently in the back arc of the Aleutians. Then we have a detached setting here. In Japan, the Japanese islands are in fact continental crust that were once connected to Asia mainland, and back arc spreading has formed here the Sea of Japan, and we can see here in the orange colors a young oceanic lithosphere has formed. At the moment there is not much back arc spreading taking place in this area, but we can see historically that was so. And we see here oceanic lithosphere that is only a few tens of million years old. Migratory plate margins are seen along the Marianas and the Tonga Kermadec island arcs that are also here in the Western Pacific, and we see the subduction of Pacific oceanic lithosphere in green color here. This is fairly old oceanic lithosphere of Cretaceous and up to Jurassic age, and its subduction triggers spreading in the back arcs, and we see here in orange colors young oceanic lithosphere forming by back arc spreading. Along continental margins, of course, we also can have convergence, and here are two settings that are different and that are tectonically important: the non-contracted or extensional versus the contracted setting. We see here subduction along a plate margin, a continental margin forming a volcanic arc. We see here various structures that we are going to discuss in more detail. And we see here in the continental back arc, extension is taking place, and basins are forming that may develop to the entire disruption of the continental lithosphere and to the formation of an oceanic back arc basin. In contracted settings, we see just the opposite. We see here crustal thickening in the continental back arc, and we see thrusts and fold belts are forming, and a foreland basin develops on the continent side of these fold and thrust belts. Examples for these settings can be found obviously in the Andes, which show a contractional back arc. In the Andes we find fold and thrust belts in the Sub-Andean ranges, which are most prominently developed in northwestern Argentina. We find an extensional continental back arc related to the subduction of oceanic lithosphere that is part of the Indo-Australian plate. The tectonic settings that we just have discussed have in common that oceanic lithosphere is subducted underneath another lithospheric plate. And let's see how this is initiated in the first place. If we have a continental margin that grades into an oceanic basin, oceanic lithosphere, we might find in a situation where convergence is initiated by large-scale plate movements that the oceanic lithosphere, because of its higher density and its mechanical strength, will be subducted underneath the lower density continental lithosphere, which tends to be more buoyant. And this shows us that the initiation of subduction, as we see it here, is essentially density driven and is depending on the different rheology of oceanic and continental lithosphere. We see here we see here that a steep fault, thrust or reverse fault is initiated, where we start to subduct the oceanic crust and the underlying lithospheric mantle. This will initiate forming a trench and may convert a passive margin into an active continental margin. In intraoceanic settings, transform faults can form important structures along of which subduction is initiated. We know that transform faults are plate margins. They can be of substantial length, up to thousands of kilometers. And across transform faults, we find older plates border a younger oceanic plate. The age of the oceanic plates plays a role in thickness and in density. Younger plates are hotter and therefore they have a lower density and they are thinner, whereas older plates have a higher density and tend to be thicker. If convergence takes place along such a boundary, the higher density and thicker oceanic plate tends to be subducted. And a similar situation is created, as we have seen along a former passive continental margin. Subduction starts along the pre-existing transform fault, which now is reactivated as a reverse fault where oceanic subduction can begin. Here we see in more detail the parts and features that commonly form along active plate margins. In this case, this is a continental plate margin. We see a number of different features. We see the oceanic lithosphere starts to get segmented into Horst and Graben structures here in the outer swell. We see the oceanic trench, which often contains significant amounts of young sediments. We see here an area that is called the accretionary prism, and we find here a four-arc basin that might be underlain by a sliver of trapped oceanic crust, which at the initiation of subduction stayed at shallow levels and was not pushed underneath the continent. This whole region here is called the forearc. It is on the ocean side of the volcanic arc, which forms as a result of magma production, which is related to the dehydration of the subducting oceanic crust. The rise of the outer swell is a response to elastic flexing that results from the bending down of the lithosphere into the subduction zone. And this is in principle an elastic response, but when the elastic limit is exceeded and permanent deformation takes place, we might form extensional faults in this area, creating these host and graben features that we see here. The accretionary prism consists of soft sediments that are scraped off the oceanic lithosphere. We see here this light gray layer that represents soft sediments, pelagic sediments that have accumulated over time on the oceanic crust itself, on the basaltic, volcanic part of the oceanic crust. Now these sediments are largely unconsolidated, they are water saturated, they are soft, and they have a low density. Such material cannot easily be subducted, and therefore in the area that we see here, where the oceanic lithosphere is pushed underneath the overriding continental crust, this soft sediment cover is scraped off and is pushed along thrust and reverse falls onto the oceanic plate with a top to the ocean transport sense. This can create the accretionary prism, which can reach a substantial size and dimension, and very often these pushed up sediments, semi-consolidated sediments, might reach a height that comes close to the sea level, as we see here. From the slope of the accretionary prism, often turbiditic sediments are mobilized and they can accumulate as trench fill, as we see here. The accretionary prism also forms an important function in the creation of four-arc basins, because we see here the triangular wedge of the accretionary prism forms the outer boundary of four-arc basins, which form a sedimentary environment that is very different from the open sea. This is often a shallow marine basin in which shallow water sediments can form. These four-arc basins are between the top of the accretionary prism and the coastline. However, not all convergent continental margins show all these features. We might find that most of them are absent. No four-arc basin, no accretionary prism. And this depends on the nature of the oceanic lithosphere that is undergoing subduction. If this oceanic lithosphere has formed at a nearby mid-oceanic ridge and accordingly is very young, there will be no time to accumulate pelagic sediments of any significant thickness. And if there are no sediments on the oceanic crust, then we also cannot form an accretionary prism. If we don't form this prism, we cannot form a four-arc basin because it requires the presence of a prism as an oceanward boundary. Also, if there is no prism, we will not find these turbiditic sediments that form the trench fill. So, accordingly, if we subduct young oceanic crust, particularly when the continental margin is in arid climate zones, we will not find many sediments forming in this area. The crust itself might be barren or might show only very thin oceanic sediments, and then the accretionary prism will be small or will be missing, the four-arc basin will not form, and there will be no soft sediments in the trench. An example for such a situation are the central Andes and northern Chile, for instance, where young oceanic lithosphere is subducted. The mid-oceanic ridge is not too far offshore in the Pacific, and the climate situation on the continent in northern Chile is very dry. There is the Atacama Desert, which is one of the driest places on Earth. Accordingly, very few sediments from the continent will be brought into the trench region. Let's have a brief look at the forces that control subduction along active continental margins. And I'm not going to talk about each and every of these forces here. Two are important: the ridge push and the slab pull. The ridge push depends on how fast oceanic crust is generated along mid-oceanic ridges. And some mid-oceanic ridges are spread at 10, maybe 20 centimeters per year. Others might only spread 2 or 3 centimeters per year, and this rate might vary over time. However, the generation of fresh oceanic lithosphere along these mid-oceanic spreading centers will control how fast the plates move sidewards, and accordingly this is the driver of the subduction rates. This coincides obviously also with the movement vector of the overriding continental or oceanic plate on top of the subduction zone. Then we have the force of the slab pull. Once we have initiated subduction, then the mineral assemblages that form at the mid-oceanic ridge will change with depth due to increasing temperature and due to increasing pressure. And once they get deep enough, the basaltic rocks and gabbros of the oceanic crust will convert into eclogite, and eclogite has a significantly higher density than normal basaltic oceanic crust. This increasing density will increase the pull of the downgoing slab. That is our slab pull force. Another factor that is important and that controls the tectonics in the back arc and the arc and along the subduction zone is the feature of rollback. We have covered this briefly in the first year course. Let's look at that again because we will later see it's a very important process. We have seen at the initiation of subduction a new trench might form, and subduction might then progress with the consumption of oceanic lithosphere underneath the overriding plate. And this is essentially density controlled. The oceanic lithosphere, when it's bent downward, will show this self-enhancing subduction. The slab pull force, ridge push and vertical component are exerting movement vectors that are important. One of them is horizontal, that would be the ridge push force, but here we then have a vertical component which is density and gravity controlled, and the force of gravity exerts a vertical movement component onto the subducting plate. Between these two vectors we will control the subduction angle, and we will initiate the rollback movement, because if the downgoing oceanic lithosphere is exposed to this downward movement, it will sink while being pushed downwards. This will move the position of the oceanic lithosphere over time from such a position into such a position. And of course we cannot create a gap between the overriding plate and the subducting plate. And that means the arc and the overriding plate will close this gap and move forward towards the ocean. This migration of the trench and the magmatic arc towards the ocean in response to this downward vertical movement of the subducting plate is what we call rollback. This illustration that I use here comes from Marshak's 2012 textbook, Earth Portrait of a Planet. I believe there are Van der Ploem and Marshak in their book on Earth structure offer a very similar illustration that we see here, with the subducting plate at time 1 in an earlier stage moving towards the ocean, followed by the overriding plate and the trench position at time 1 and time 2. Again, this is what rollback achieves. How can we use rollback and plate movements to explain different types of arc and back arc tectonics? On the first slides we have seen different types of convergent margins. Some show contraction in the back arc, others show extension, and again other back arcs are tectonically stable and neither extend nor contract. The key to the understanding of these different back arc tectonics has a lot to do with the rollback and with the movement vectors of the overriding and the subducting plate. 3 examples are offered in Van der Ploem's and Marschak's textbook, which presents more detailed information than what I'm going to present in this short video. We see here a first case of a continental margin, and we see here contraction is taking place in the back arc and the overriding continental plate is substantially thickened. How does that happen? This depends on 2 factors. It depends on the movement vector of the overriding plate, which is an independent lithospheric plate with an independent movement vector. And if this movement vector points in the same direction as the rollback, but is larger, that means the overriding plate moves faster towards the ocean, then the rollback can move the subducting plate out of the way. We will find that the overriding plate has to respond to this movement difference by contraction. This is a situation that we find in Andean type plate margins. We have seen the Andes are an example where the Sub-Andean ranges form as a fold and thrust belt, as we see here, as a response of back arc contraction. So, if the overriding plate moves in the same direction as the rollback, but is faster, we will produce an Andean type plate margin with back arc contraction. In addition to the Andes and the Sub-Andean ranges, also the Cape Fold Belt in South Africa is such an example of a contractional fold belt and a foreland basin. The foreland basin is not shown here, but typically we will form a shallow sedimentary basin on the continental plate on the far side of the fold and thrust belt. And the South African example of the Cape Fold Belt shows it with a large intracontinental basin of the Karoo. In this case here we see a situation where in an intraoceanic convergent margin setting the back arc is undergoing extension, and this extension has reached the stage where a new oceanic crust is formed along mid-oceanic ridges. This process, as we will see later, is controlled by the subduction of the lithosphere underneath this arc. Specific movement vectors are required to achieve back arc extension. The overriding plate needs to move in the same direction as the rollback, but is slower, or it even moves in the opposite direction. The Mariana Island arc is one of the possible examples where processes like that take place. Of course, the island arc has to remain on top of the subducting slab. And the only response, if the overriding plate is slower than the rollback, is back arc extension. And this extension can lead to the entire disruption of the back arc lithosphere and the formation of a back arc basin. The Tonga-Krema-Dek island arc could be the second, perhaps even more appropriate example. In principle, this back arc extension also works when the overriding plate is continental lithosphere. We have been talking about the Java-Sumatra example. Here we have subduction of the oceanic lithosphere underneath a continental margin, and in the back arc of the islands of Java and Sumatra we find continental back arc extension, which has not yet reached the stage where oceanic crust would be generated. The third case that we see here would be a back arc that is tectonically stable. We see here that the overriding plate has the same movement vector and the same velocity as the rollback. And if these two vectors are of equal magnitude and equal direction, then the back arc will be stable. The overriding plate will simply follow suit the rollback at the same velocity, and no differential stresses will be generated in the back arc that would allow either extension or contraction. This is currently the case for the Japanese islands. The back arc of Japan between the Japanese islands and mainland Asia are tectonically fairly stable. But in the past that was not the case, because separating the Japanese islands and mainland Asia, we find an extinct ridge and a narrow oceanic basin that has formed, indicating that in the geological past this was an extensional back arc during which this narrow oceanic basin formed. We now have seen different examples and descriptive velocity vectors that generate contractional, extensional or stable back arcs. Now, why is that so? Why do we form sometimes the one and sometimes another version of back arcs, or we even change over time, like in the example from Japan, extensional to stable, or perhaps even extensional stable to contractional back arcs? The key to the understanding this process and these tectonic switches from one setting type to another is the subduction angle. We see here subduction angle alpha describes how steeply the oceanic lithosphere is subducted, and that of course depends on the magnitude of the vertical vector during rollback. If this vector has a larger magnitude, this indicates that we are subducting oceanic lithosphere with a higher density, because the higher the density, the steeper the subduction angle will be. And so if the subduction angle depends on density, then we need to ask what controls density, and of course the density of oceanic lithosphere depends on temperature. High temperature oceanic lithosphere has a lower density than low temperature oceanic lithosphere, and the temperature in turn is controlled by the age of the lithosphere. Accordingly, old oceanic lithosphere that has existed for a long time because the mid-oceanic ridge is far away from the subduction zone will be colder, will be older, and will have a higher density, and accordingly will be subducted at a steeper subduction angle. Here we see an example of steep subduction underneath a overriding continental lithosphere, and we see that along this steeply subducting oceanic lithosphere, astenospheric mantle material is dragged down. Of course it has to be replaced, and we see here from the movement vectors the astenospheric material will undergo a circular mass movement where asthenosphere is brought downwards, will heat up, lose density, and accordingly rise again in these convection cells that form underneath the back arc. If such hot astenospheric material rises, decompression melting will form fresh plutonic rocks. We will have a very substantial heat input in the overlying lithosphere, in this case a continental back arc, and that will thin out the back arc and lead to back arc extension, simply in consequence of the convection that is happening in the asthenosphere underneath. This will be different if the subduction angle is shallow. If we are subducting hot and young and low density lithosphere, the subduction angle will be significantly shallower compared to old and high density lithosphere, and the subducting plate will get in the way of any possible back arc mantle convection. So the back arc convection that we see here only can form if the subducting plate is sufficiently steep. In this case, this will not be possible. What happens instead is that we generate with a shallow subduction more friction because the contact surface between the overriding plate and the subducting plate is significantly larger. This creates contractional forces in the overriding plate. We are not generating significant heat influx into the overriding plate, which stays relatively cold, but is undergoing the horizontal contraction. That moves the arc from an initial position further inland, and we will find thickening and thrusting in the back arc. This is where back arc fold and thrust belts are forming. We also might form foreland basins further inland as a result of elastic flexing, which is a response to the contraction in the arc and back arc region. Now, of course, over time, the age of subducting lithosphere along a active plate margin can change. We might find that at some time old oceanic lithosphere is subducted, and with the approach of a mid-oceanic ridge that comes closer and closer, the lithosphere will become younger and hotter. This will change the subduction angle, and if it becomes shallower, perhaps this back arc extension will stop and the back arc will become stable because of reduced or absent convection in the back arc asthenosphere. And if eventually we are subducting very young oceanic lithosphere because the mid-oceanic ridge is not too far offshore anymore, the initially extensional and later perhaps a stable back arc might convert into a contractional back arc. This change in subduction angle will change the back arc tectonics, and this is what forms back arc mobile belts. Back arc mobile belts, particularly well known from continental crust, show periods of extension, stability and contraction, and that can change over hundreds of millions of years in a cyclic way. We call this tectonic switching. And if you want to learn more about the subduction in back arcs and mobile belts, there are beautiful papers. One of them is Hindman et al. In 2005 in GSA Today, and another paper from 2006, the thermal structure of subduction zone back arcs by Claire Curry and Roy Hindman. I also want to mention that back arcs, particularly continental back arcs, are of economic significance. We have seen that during extensional periods of back arc mobile belts, we introduce a lot of heat into relatively thin and hot continental crust. If you introduce a lot of heat into crust, you will initiate magmatic activity. You also might initiate substantial fluid circulation that is suitable to leach economically important elements and to enrich them in ore deposits. This is, for instance, related to the formation of SEDEX deposits and also volcanically hosted massive sulfide deposits. Many of these deposits form in continental back arcs, and sometimes such back arcs might be flooded, sometimes they might also be on land, but this is a process that continuously happens wherever you have continental back arcs under extension. Accordingly, this is an example where plate tectonic processes are instrumental in the origin of ore deposits. If you want to know more about this, I recommend this paper in Economic Geology from 2010 that deals specifically with this aspect of ore body formation. Thank you very much.